Hi guys, welcome back to ASFC Chemistry. Now for this one, this is more of a webinar style video which has got lots of content, so there's going to be timestamps in the video description if you want to be taken to any particular reaction. We are looking at the first year organic chemistry reactions, but I'm also going to look at the three mechanisms, two of which have curly arrows, and we're also going to look at purification of organic liquids because that comes up in the first year spec. So check the video description if you want to know at what points we're covering each of the reactions. Otherwise, I'll be referring to this OCR synthetic pathway sheet throughout this video, which you can also find a link to in the video description. Let's get started then. The sheet I'm going to refer to throughout this is available on the OCR website, and it's their aliphatic compounds reaction pathway sheet. I'll put the link in the video description for this. The first one we're going to do is the Alkane to Haloalkane, which is often found in the Alkane notes, and it uses a halogen and some UV light. Now, there is actually a reaction mechanism tied to this, which is radical substitution, that I'll go through alongside this reaction. We start off with our carbon atom that's going to be bonded to any length of carbon chain. It could be cyclic, it doesn't really matter. I'm just going to use a bog standard methane for this, but all those H's could be absolutely anything, so long that one was still remaining. I still needed one CH bond on the molecule at the very start, but the rest, it could be part of a cyclic ring. It's not going to be aromatic, we don't see that come up in this type of reaction, and any of the halogens can be used. The whole premise of the reaction is that in the presence of UV light, one of the CH bonds will be substituted as a CCl bond instead. And we also make some HCl, or of course HBr, HI, depends what you're using. Further substitution is a problem with this reaction because there are remaining CH bonds on our molecule at the end, so that chloromethane product, it's still got CH bonds, and so what could happen is that could go back in and you could end up with another of the CHs becoming CCLs, and you need to know that that's an issue with this. Like I said, the mechanism is called radical substitution, and as you can see here, I'm outlining initiation to begin with. There's no curly arrows in this mechanism, but it is a good example of homolytic bond fission. This initiation step is exactly that. We've got Cl2 forming two Cl radicals here in the presence of UV light. And it's the UV light that provides the energy to break that covalent bond in that homogeneous fashion. We've also got here then our propagation stage, which we see the alkane reacting with the halogen radical to form an alkane radical and some HCl. And then in the second stage, the alkane radical that we actually made reacts again with the Cl2 in this case, but it would be whatever halogen is from the overall equation, to make our target organic molecule and reform the halogen radical. The third stage of the mechanism is called termination. And termination takes two of the radicals that we've made, one of each, and it reacts them together to make the target organic molecule. There are alternative termination steps where you can effectively take any of the radicals and combine them together, so two of the Cl radical or two of the alkane radical, it doesn't really matter, it's perfectly fine, but these are often kind of like, accept these alongside the original one that I wrote there for termination. The next reaction from our summary sheet is the alkene to the alkane. So this uses hydrogen and a nickel catalyst that we'll talk about once we've written out the reaction equation. So I can't make methane from this, which I was using in the last set of reactions, but I can make ethane. We'll call this reaction 2, and we're going to see 11 in total today, with one of these reactions having a subsection as well. So I take any sort of alkene, I just need the alkene functional group inside the molecule, and it does work with multiple alkenes, and for every alkene bond I have, I react it with a molecule of hydrogen. This is all gaseous, by the way, as well. The temperature for this is very high, and my catalyst here, the nickel, is a solid, and it's in a different phase from the reactants, it's in a different state, and so that means the nickel is a good example of a heterogeneous catalyst, and it's one of those that you can go to as a quick example. Similar to iron in the Haber process, we've got a good example there of a heterogeneous catalyst in our iron. And we're back on the summary sheet. This time we're going to look at turning an alkene into a haloalkane. Now on the actual summary sheet it only says hydrogen halides here can be used as reactants, but you can actually react the alkene with a halogen, so like an X2 formula, like Br2 and Cl2. So I'll use bromine as a first example of that, and we'll talk about why I've used bromine and also if this does vary the mechanism a little bit throughout this. So you can see here for this first one, what I've chosen to use actually is an example of propene, because I want to talk about carbocations throughout this page. And I'm using bromine here because it's a little reminder that bromine water is the test for an alkene functional group. It decolorizes the bromine and you need to be aware of that. Now here what happens is basically each carbon from the double bond ends up with a bromine. So it's different from a hydrogen halide reaction, and we only get one product. And so the carbocation intermediate step is completely irrelevant here so long as we show it properly. So we've got our alkene here at the start of our electrophilic addition mechanism, so there's a mechanism associated with this reaction. The double bond induces a dipole on the halogen molecule because otherwise it wouldn't naturally have one occurring, and we see that the double bond reaches out to the delta positive bromine, and the bond between the two bromines breaks heterolytically with both electrons going onto the bromine on the right hand side of my diagram. I've chosen to make a primary carbocation intermediate here, but it was irrelevant which one I chose to actually synthesize for our intermediate step, because both carbons end up with a bromine at the end, so really it doesn't make very much difference at all. You can see here the product that I actually make is 1,2-dibromopropane, and it really doesn't matter which carbocation I've used for this particular example, but it will matter if I was using a hydrogen halide in what we're going to call reaction 3B, which was actually the original type suggestion on the sheet. So you can see here I've gone for the same alkene at the start as last time, but this time I'm reacting it with HBr. Now, this time we're going to see two different possible organic products made because we use different carbocation intermediates. In the exam, if you had to represent that both products were possibilities, you would actually write out the equation twice. You wouldn't do what I'm going to do here and put or between the two molecules. In the exam, just make sure you do two separate reactions. But the whole premise here is you've got an H and a Br going on, and you can either have the H going on the first carbon from the original chain and the bromine on the second, or vice versa. Now, there is a major minor split as well between these two molecules, and we need to be aware of what that is. Here you can see that I'm going to label up the first molecule I wrote down as the major and the second as the minor, and that's because a majority of the final solution is that first structure. So why is that? Well, let's have a look at the carbocation intermediate that would be used to synthesize this major product. I'm basically taking off the bromine and putting a positive charge on the carbon where the bromine is eventually bonded, because I'm familiar that that would be the final step of the mechanism, and I'll show that stage later as well. Now, because the bromine was taken off the second carbon along in a 3-carbon chain, the carbon that's on the original structure there with the positive charge is bonded to 2 other carbon atoms directly. And we could redraw that as perhaps 2 R groups, or 2 rests of the molecule as well, and then we've got just 1 H on that carbon. Now that means that that carbon is an example of a secondary carbocation intermediate, whereas the structure on the right hand side, which would have been the alternative minor products intermediate carbocation, is actually only a primary carbocation, because the carbon with the positive charge is only bonded to 1 other carbon directly and 2 H's. The secondary carbocation is more stable than the primary. Hence, a majority of the time, when the mechanism has to make a choice, if you will, it's going to go in the direction which is more stable, and we end up with that 2-bromopropane being the more common product. What I'm going to outline for you here on the left is actually the mechanism for the formation of the major product, just so you can see this selectivity in action. Alright, so going back to our summary sheet once again. And this time we're going to keep with our haloalkane, but we're going to go down here on our summary sheet and we're going to use some aqueous sodium hydroxide and we're going to form an alcohol. Now this works for any haloalkane and it will form any classification of alcohol, just to make that absolutely clear. We could end up with a primary, secondary or tertiary alcohol from this, and obviously those structures of alcohol vary in how they are going to react, but it's important that you realise this is a way of synthesizing any one of those. It's completely dependent on our haloalkane. This is our fourth reaction that we're going to study, and I'm going to go to a template here for the rest of these as well. Instead of showing a huge chain coming off the carbon here, I'm going to show an R, but I do want to be really clear that very often with these, those H's could also be R's as well, although we'll see that we have got limitations when we do the oxidation of alcohols further into this webinar. Now, the sodium hydroxide, I've put the state symbol on that just to emphasize the point that it is meant to be aqueous, and you can see wherever the CX bond was, I've now just replaced it with an OH. I also make some sodium chloride or sodium halide, it depends on what halogen you've actually got in here, product alongside it. Now, as a practical point for this one, we need to be really careful that we use a reflux instead of a distillation. This did come up in an exam. You can't suggest a distillation for this because the product containing an OH functional group is going to have hydrogen bonding between its molecules, and so it's going to have a higher boiling point than the reactant. The reactant is more likely to evaporate and be collected if we do a distillation. Going back to the summary sheet, what we're going to do now is effectively reverse the process we've just done, but with obviously very different reagents. We use a sodium halide and H2SO4. So this is acidified sodium halide. The reaction equation, you can use just a hydrogen halide, but I'm going to split up the ions to show you the two sources of this. And like I said, it's effectively a reverse of what we've just done, but it's our fifth reaction, and we're going to use R again. You can use any classification of alcohol for this as well. Again, I just want to make that point because we're not actually looking at interfering with any of the H's or R's. We're just swapping an OH for a CX bond. That's all we're doing. The H plus in this equation is provided by the H2SO4 from the summary sheet, and the Cl minus is from the NaCl, or obviously it would depend on what halide ion you want present in that. Like I said, as you can see now in the structure of the product, all I'm doing is I'm swapping the COH for a CCl in this case, and I also make some H2O. Now this mixture is a really good opportunity to bring up the other part of organic chemistry that sometimes gets overlooked, which is purifying organic liquids. Now, for purification of organic liquids, we need to know three essential components to the purification process. This is a really good example that did actually come up. I think it was the 2018 exam set had literally this exact haloalkane and water mixture at the very end. And you had to incorporate three different separating techniques for your purification into your level of response answer. The first technique is a separating funnel, and the reason we do this is it will separate the organic from the aqueous. But it isn't perfect, so what I would then use is a drying agent. Now, the drying agent example here that I want to give is anhydrous CaCl2, but you can also suggest anhydrous MgSO4. Check your specification, it does give you both of those options, but you do need to make sure you mention that it's anhydrous. Finally, the third technique is a redistillation. This is often actually done at the boiling point of the target organic molecule. Read the exam question very carefully to see if they provide you with that information. Just before we move on, I do want to emphasize here, look at what groups we've changed. So we are going back and forth here between our halogen and our OH being on the molecule. So this is a good set of reactions to revise together. Also, reaction 4 is the only one out of these two that actually carries with it a mechanism. The mechanism is nucleophilic substitution. Now, for nucleophilic substitution, draw your molecule out as it appears in the exam paper. Don't abbreviate. I'm using a template here for you. And to give yourself a bit of room, I always overextend the carbon halide bond just here. Our nucleophile is OH-, and from the middle of the lone pair, always try and be consistent with that, we attack the carbon atom that's delta plus and break the bond heterolytically onto the chloride in the CCl bond, which is delta minus. This produces our alcohol product, and don't forget to always show that Cl- with it as well. Going back to our summary sheet just here, now we've seen the haloalkanes used quite a bit, but we just had a bit of alcohol reactivity there, so what I want to do now is jump into the alkenes forming the alcohols with H2SO4 in the form of steam and a phosphoric acid catalyst. They're quite flexible with the phosphoric acid catalyst in the exam. You would be able to use H2SO4 as well, but I think it's good for our sixth reaction just here to be consistent to the summary sheet. So I've got my alkene, and again, the alkene could have any length of chain. It could be anywhere in a molecule, so be nice and flexible with that. It isn't always going to be ethene, perhaps, for instance. And I'm emphasizing here that the H2O is steam, just putting that state symbol on to make the point that's made on the previous summary sheet. Now, what we form here is an alcohol, and again, we can form multiple classifications of alcohol just here. I don't want to limit our understanding to primary and secondary. A tertiary is an option from this. The acid catalyst here, the H+, is shown over the arrow just as almost a reminder to help you out, and really do go with the previous page if you can of H3PO4 phosphoric acid. Going back to our summary sheet, so our next logical thing to do, since it's on there, is to reverse what we've just done. So this time we're going to use H3PO4 or H2SO4, so effectively strong inorganic acids, and a bit of heat here as well, turning an alcohol back into an alkene, and this is our seventh reaction to consider. Now, this one carries with it a little bit more information. I'm going to go through a general structure of this to begin with, using our alcohol. Now, we need the carbon adjacent to the carbon with the OH to have a hydrogen available as well. Otherwise, we can't form the bond between the two that we need, so that's forming our alkene bond. Here, for instance, you can see what I'm going to do is form the obvious connection between the two carbons that I drew in the straight line of the starting alcohol structure, and I kick out some H2O. But like I said, you can end up with some sort of extra complications with this. For example, you can end up with some isomerism taking place. And this is both types of isomerism. You can actually end up with structural, and you can end up with stereoisomerism. The example I'm going to use for this, and it is a bit time consuming drawing this out all the time, but I'm actually going to use here butan-2-ol as my example of a molecule that can end up with some isomerism in the products. So my first possible product here then, and don't forget I'm in the acidic conditions from the previous page, is that I put the double bond between the two carbons on the left-hand side of the original molecule. So it obviously has to be one of the carbons that originally contained the OH, and you can see the products that I've got here is but-1-ene. Now this is, as you can see, numbered out between carbons 1 and 2, but the alternative then would be to put the double bond between carbons 2 and 3 instead, and this is where the complications start to occur a little bit more. Now the first obvious difference is going to be that the double bond is further up the chain from the original molecule, and so our first obvious comparison is going to be that we've got structural isomerism between these two structures. Don't forget that H2O is always released for either of these as well, and I'm just showing that in the brackets because I'm not writing full equations for these reactions here. These two, so I've got my but-1-ene and I've got my but-2-ene, are structural isomers of each other. So they've got the same molecular formula but different structural formula, and that makes them structural isomers. The keen-eyed ones amongst you will have noticed that the but-2-ene here has also actually got some stereoisomerism. So the stereoisomerism possible in the but-2-ene is EZ isomerism and cis-trans. If you check the cards on this video, there'll be a link to a description that supports the differences between these two. But here on the left, what I'm going to give you are the structural formulae of the E and Z isomers, also tied to cis-trans here. And if you're unsure how we assign Z or cis, or how we assign E or trans, or whether Z and cis are always together, I recommend you check out the cards on this video at the end and take yourself to that EZ difference video. Now, you also, when you name the but-2-ene, you can put E or Z or cis or trans at the start of the name, and this stereoisomerism is emphasized in that naming system. Back to our summary sheet, and we've been centering around the alcohols for some time now, so let's have a look at how these react. And specifically for the alcohols, I'm going to take the primary first. So I'm going to take the primary alcohol, and I'm not going to do any sort of reduction here because that's second year. I'm just going to concentrate on oxidizing. So the first oxidation I'm going to do is going to take the primary alcohol through to an aldehyde. I'm also going to look at some point during this how the primary alcohol goes to a carboxylic acid, and I'm also eventually going to take the aldehyde and turn it into a carboxylic acid as well. So I realized that was a lot of different oxidation descriptions just there. Let's have a go through it one step at a time, starting here with our 8th reaction. So for our 8th reaction, we're going to have an alcohol to start off with, which absolutely must be primary. So it's a primary alcohol because the carbon with the OH functional group is itself bonded to one other carbon atom and 2 hydrogens. The one other carbon atom here represented by the R. Now, using a distillation and an oxidizing agent, which is what the O in square brackets represents, I can go from a primary alcohol to an aldehyde. Secondary alcohols cannot become aldehydes, and tertiary alcohols do not oxidize. I've also got some water products here, and so I've got my O in square brackets balanced just like an oxygen atom, but remember the O in square brackets represents the acidified sodium or potassium dichromate. Specifically as well, the acid is H2SO4, although you can just represent it as an H+, and don't forget that the slash doesn't mean instead of, it means with. So that's acidified sodium dichromate, as you can see on screen now. That oxidizing agent provides us a very helpful colour change for our distillation, which is orange to green, or OMG, orange makes green, if you're looking for a way to remember this. We can see here as well that this aldehyde has got a low boiling point because it doesn't have hydrogen bonding between its molecules. So a distillation is a good suggestion for this because it allows our aldehyde to evaporate, cool, condense, and be collected immediately. Now, an alternative reaction that we can see here is when we take the primary alcohol, and don't forget that I'm using the primary alcohol in the first reaction on this sheet, but also in the second just here. And if I take this primary alcohol and I react it with 2 moles of the oxidizing agent this time, and I fast track it all the way past the aldehyde, right the way through to a carboxylic acid, heating under reflux. Now, a reflux is different because any vapors released are condensed and returned to the reaction vessel for further reaction. They aren't condensed and collected immediately like a distillation. And as a result, I end up with the carboxylic acid product using the same oxidizing agent, but in different apparatus. And again, we've got some H2O. Alright, now going back to our reaction summary, I'm going to look at our 2 final reactions. The first one is actually not the one I'm highlighting up here. The first one I'm going to do is a secondary alcohol to a ketone, but then we'll look at the one I just highlighted then, which is going to be the aldehyde through to the carboxylic acid. So this is our 10th reaction, and secondary alcohols are the only classification of alcohol that can oxidize to a ketone. Secondary alcohol is when we've got the carbon with the OH functional group itself bonded to 2 other carbon atoms directly and 1 hydrogen. So that classifies it as a secondary. Tertiaries, don't forget, won't oxidize, and so we aren't going to see any tertiary alcohols here becoming anything with a C double bond O group. So the secondary alcohol reacts with exactly the same oxidizing agent, and really we should do this reaction heated under reflux. Although it would work under a distillation, your OCR specification really does insist that you learn it's a reflux. I just wanted to put that in there as a little bit of extra information. The ketone product here is different from an aldehyde, but it looks very, very similar. And actually, if I had an aldehyde, a ketone, if I had 2 of those with the same length of chain, so for example, propanal and propanone, they would be structural isomers of each other. They would have the same molecular formula but different structures. One would be the aldehyde and one would be the ketone. The ketone carbon is never at the end of the chain, whereas an aldehyde carbon is always carbon 1. The ketone carbon is always going to be inside a chain, and that's a nice notable difference between the 2. As we can see here, the ketone was made from a secondary alcohol. the aldehyde was made from a primary alcohol, and as you can see now, for our 11th and final reaction, the aldehyde, if I bring it up again, so taking the product from reaction 8 at the top of our screen that we were using, and turning this into another reaction, I'm going to take the aldehyde and react it with more of the oxidizing agent, this time under a reflux, and I can form a carboxylic acid, but the carboxylic acid is the only product in this reaction, and as you can see, compared to the others that you've hopefully made a list of, it's the only oxidation reaction that produces only one product. All the others produce two different products, one of which always being H2O and the other being organic. So just to make it really, really clear, because I can appreciate I sort of jumped the gun a little bit here with the highlighting, the reaction that we did, which was number 10, is taking the secondary alcohol and making it a ketone using exactly the same oxidizing agent. And the one that I did just prior to that, which was, just after that, which was number 11, is taking my aldehyde to carboxylic acid, heating under reflux. I'm using the same oxidizing agents all the way through here. I can use acidified sodium dichromate or acidified potassium dichromate. It doesn't matter which one I've gone for there, just as long as it is actually acidified, because I do find people forget that. Also, make sure you really know the difference between aldehydes and ketones, because otherwise you're going to struggle with the second year part of the course when we look at reduction. Okay guys, thanks for watching this video. If you click the eye at the top of the screen on this video, you'll be taken to the cards, which has got lots of links to other videos, to associated content, and also you've got the links on screen now, which will take you to those videos or playlists straight away. Until next time, happy revising.